Hello. I'm going to go through the OCR 2022 AS Level Chemistry Paper 2 Depth in Chemistry. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. Question 1 is about the citric acid contained in lime. In part A, there is a statement saying that citric acid is a weak acid and it followed by two questions. In the first question, we need to define acid. Acid is a substance that provides protons or ions H+. In question 2 we are asked by the definition of weak acid. Weak acid is an acid that partially dissociates. In part B of question 1, we are given the details of titration by a student to determine the mass of citric acid in a lime. The juice of 2 limes are diluted to 250 cubic centimeters with water. 25 cubic centimeters of this solution are titrated with 0.8 molar sodium hydroxide. The student performs a trial titration, followed by 3 further titrations, and we are given a diagram showing the volumes used. Each reading is measured to the nearest 0.05 cubic centimeter. In the first question of this part, we are given a table to record the student's burette readings. We also need to calculate the mean titer, to the nearest 0.05 cubic centimeter, that the student should use to analyze the results. Starting with the initial reading of titration 1, we can see that the volume given by the center of the meniscus is between 0 and 0.1. As the volume is measured to the nearest 0.05 cubic centimeter, we can say that this value is 0.05 and fill the table. We now move to the final reading in the first titration. The volume is between 27.3 and 27.4. We can say that it is 27.35, and add this result to the table. With these two values for titration 1, we can find that the titer required in titration 1 is 27.35, take away 0.05 equals to 27.30. We now move to the second titer. The initial reading is 0.1, then, we add the value of 0.10 in the table. The final reading is between the 27.6 and 27.7 mark, we add the value of 27.65 in the table. The titer in titration 2 is 27.65, take away 0.10 equals to 27.55. We move to the titration 3. Initial reading is between 0.4 and 0.5. We add an initial volume of 0.45 in the table. The final reading in titration 3 is between 27.8 and 27.9. We add 27.85 in the table. These results give as a titer of 27.85, take away 0.45 equals to 27.40. Titrations 1 and 3 are concordant, as the results are within 0.1 cubic centimeter within each other. Titration 2 gives a result outside the 0.1 cubic centimeter range and it is considered not concordant, therefore we discard it. The mean value for titrations 1 and 3 is 27.35 cubic centimeters. We are now in the second question of part B from question 1. We are given the equation between the citric acid and the sodium hydroxide and the molecular mass of the acid. We are asked to calculate the mass in grams of citric acid in 1 lime, assuming that citric acid is the only acid in lime juice. I copy from the relevant information that we need from the first question. We have used 27.35 cubic centimeter of 0.8 molar sodium hydroxide. This is equivalent to 0.02188 mole of sodium hydroxide. From the provided balanced equation, we know that each mole of citric acid requires 3 mole of sodium hydroxide, therefore the number of mole of citric acid titrated with 0.0218 mole of sodium hydroxide is 0.007293 mole. However, these 0.007293 mole of citric acid were obtained in a 25 cubic centimeter sample taken from an original 250 cubic centimeter solution. The number of mole in the 250 cubic centimeter original solution is 10 times more, that is, 0.07293 mole. As 0.07293 mole of citric acid were provided by 2 limes, we can estimate that each lime contains half of this amount, that is 0.036465 mole of citric acid per lime. With the given molecular mass of the citric acid, we obtain that the number of grams of citric acid 1 lime is 7.001. Rounded to 7.00 grams. In Part C of Question 1, we are asked how the student could modify the method using a sodium hydroxide concentration of 0.2 molar instead of using 0.8 molar. The student should aim to have the same titer as in the original method. As the concentration of the sodium hydroxide has been reduced 4 times, to keep the same titer, the concentration of the acid should be also reduced 4 times. This can be achieved by, for example, diluting to 1000 cubic centimeters the juice of the 2 limes instead to 250 cubic centimeters. In Part D of Question 1, we are given the structure of malic acid. We are asked to write the balanced equation and the structure of the organic product obtained when the malic acid is oxidized by heating with acidified potassium dichromate. We are asked to write O in square brackets to represent the oxidizing agent. The malic acid has 2 carboxyl groups, COOH, and 1 hydroxyl group, OH. The carboxyl groups cannot go to further oxidation, only on a few examples can be oxidized to form carbon dioxide, therefore the oxidation will be produced in the hydroxyl group. We have an oxidation of a secondary alcohol to form a ketone. Question 2 is about some group 2 elements and their compounds. In Section A, we have 3 questions about the reaction of strontium and calcium with water. In the first question we are asked to write an equation for the reaction of strontium with water. Group 2 elements react with water to produce the metal hydroxide and hydrogen gas. Therefore, the reaction of strontium with water produces strontium hydroxide and hydrogen. It should be noted that the beryllium does not react with water, and magnesium reacts very slowly with cold water but more rapidly with steam to form magnesium oxide. In the second question we are asked why the previous reaction is a redox reaction using oxidation numbers. In a redox reaction, there is a transfer of electrons between 2 species, one is oxidized, loses electrons, and the other is reduced, gains electrons. In this reaction, we have the oxidation reaction in which the strontium metal pass from oxidation state 0 to oxidation state +2 in the strontium hydroxide. In the reduction reaction, the hydrogen in the water passes from oxidation state +1 to oxidation state 0 in the hydrogen gas. In the third question, we are asked why calcium reacts more slowly with water than strontium. This is to do with heat decrease in reactivity as we go up in the group. In 3 bullet points 1 for each mark. Calcium has fewer electronic shells than strontium. Fewer shells imply less shielding of the valence electrons and more attraction by the nucleus. Greater nucleus attraction requires more energy to lose the valence electrons and therefore less tendency to react. In Question 2, Part B, we have 2 questions about the reaction of barium oxide with water, that forms a colorless solution. In Question 1, we are asked about the pH of the solution. In general, the reaction of oxides of the group 2 with water produces hydroxyl groups, OH-, giving an alkaline solution. In the case of barium oxide, it will form barium hydroxide, that is soluble in water forming a colorless solution. As we are not given any numbers for calculations or estimation, we just need to mention that the pH will be alkaline, with a pH between 8 to 14. In the second question, the student adds a few drops of dilute sulfuric acid to the solution. We need to describe what the student would observe, and give the formula of the barium compound produced. Addition of sulfuric acid will produce insoluble white barium sulfate, that will precipitate, as the barium sulfate is highly insoluble. Therefore, the observation is the formation of a white precipitate formed, and the formula is the barium sulfate. Question 3 deals with reactions of zinc compounds and zinc metal. In Part A, a student investigates the rate of reaction between zinc carbonate and dilute hydrochloric acid, and we are given the equation. The method followed by the student is: first, addition of 50 cubic centimeters of dilute hydrochloric acid into a conical flask at 20 degrees centigrade. Second, the flask is placed on a top pan balance. Third, an excess of zinc carbonate is added. And fourth, the mass of the flask and contents on the top pan balance every 30 seconds. We are provided with the graph of mass against time obtained by the student. In the first question, we are asked to explain, using the collision theory, the reaction gets slower over time and eventually stops. Collision theory states that in order to react with each other, particles must collide in the correct orientation and with sufficient energy. As the zinc carbonate is in excess, the limiting reagent is the dilute hydrochloric acid. In the initial stages, the concentration of hydrochloric acid is high, producing a large number of successful collisions in short period of time, high rate. As the concentration of hydrochloric acid reduces, the number of successful collision decreases, giving a reduction in the rate. When all the hydrochloric acid has reacted, no more successful collisions are produced, and therefore the reaction stops. In the second question of Part A of question 3, we are asked to find the rate of reaction in grams per second at 50 seconds using the graph provided. The rate of the reaction is the change of the concentration over time. It is obtained by the slope or gradient of the curve at a given time. We calculate it by drawing the tangent of the curve in that point. It is recommended to use a large line. I start by finding the point in the graph that corresponds to 50 seconds, I use yellow lines. I draw the tangent to the curve on this point, red line. I take 2 points on this line, I use as first point 0,92.4 and as second point 220,91. I get a gradient of -6.36 by 10 to the power of -3. It is a negative value because the concentration is reducing. However, you will not be penalized by giving it as a positive number. It is understood from the problem that the concentration is reducing. In the third question of Part A, of question 3, we need to sketch, on the given graph, the curve the student would obtain if the same procedure was followed, except that the 50 cubic centimeter of dilute hydrochloric acid was heated up to 40 degrees centigrade before adding the zinc carbonate. As the temperature increases, the initial speed or rate increases, indicated by a step or slope, but the final concentrations should be similar. I draw my line in red. Any curve will be valid as long as: first, the slope is stepper. Second, it levels off earlier, and third, the final mass is similar, around 91.55 grams. In section B of question 3 we are given the reaction between zinc and dilute sulfuric acid and the comment that copper sulfate is a catalyst for the reaction. The student adds a piece of zinc to each of 2 test tubes. Then, the student adds a few drops of aqueous copper sulfate to one of the test tubes, forming a pale blue solution. Finally, the student adds an excess of dilute sulfuric acid to each test tube. We have 2 questions referring to this experiment. In the first question, we are asked to describe 2 differences the student would observe between the test tubes. As the copper sulfate is a catalyst, it increases the speed of the reaction. The zinc will disappear faster and the hydrogen produced faster in the test tube with copper sulfate. So, the 2 observations are: first, the zinc disappear faster in the test tube with copper sulfate. Second, more bubbling, more hydrogen, will be produced in the test tube with copper sulfate. In the second question of this section B, we are asked to sketch an enthalpy profile diagram for the reaction with and without the catalyst in a diagram provided. We need to include the enthalpy change and the activation energies with and without catalyst. As the enthalpy is negative, minus 140 kilojoules per mole, the reaction is exothermic and the final enthalpy will be lower than the initial enthalpy. To start the reaction, it is necessary to overcome the activation energy, being the activation energy without catalyst greater than the one with catalyst. Question 4 is about the manufacture of hydrogen. In part A, we are given the reaction to produce hydrogen from methane in the industry. The industrial process is carried out at 15 atmospheres pressure and at a temperature of 800 degrees centigrade using an excess of steam. A nickel catalyst is used. We are asked to explain these industrial conditions. Looking at the data given, we can have an idea of what is required in the answer. We have that the enthalpy is positive, therefore, it is an endothermic reaction. We are also given the pressure, temperature, and excess of steam. The catalyst is mentioned. So our answer should refer to exothermic reaction, pressure, temperature, excess of steam and catalyst. I would write something like: effect of pressure, an increase in pressure will displace the equilibrium to the left, as there are more mole of gases on the right-hand side, Le Chatelier's principle. Higher pressure will also increase the rate, as more molecules will collide. However, working at high pressures might be unsafe and precautions should be taken to minimize risks. Additionally, high pressure is expensive to generate. Effect of temperature, as the reaction is endothermic, change of enthalpy is positive, an increase of temperature will displace the equilibrium to the right, Le Chatelier's principle, and it will also increase the rate, as more collisions will occur. However, high temperature can present risks and increase the production costs. The catalyst increases the rate of collisions by reducing the activation energy and helps to reduce the temperature required for the process. The catalyst does not affect the equilibrium, just allow to reach it faster. The use of the steam will displace the equilibrium to the right, as the concentration of water vapor increases. The conditions used in the industry are usually a compromise between reducing costs and increasing productivity. In the second question of Part 4a, we are given the reaction of methane with hydrogen and the concentrations in equilibrium. With the concentrations in equilibrium provided in the table, we are asked to calculate the equilibrium constant to 3 significant figures. We just need to replace in the equation of the equilibrium constant the values given in the table. I get 24.149. Rounded to 3 significant figures, it is 24.1. In question 4b, we are given the reaction of ethanol with steam to produce hydrogen and a table with the bond enthalpies. We are asked to calculate the change of enthalpy in the forwards reaction. Based on the definition of bond enthalpy, it is the energy needed to break 1 mole of a particular bond in 1 mole of gaseous molecules. The answer is straightforward. We need to calculate the energy required to break all the bonds broken in reactants and add the energy produced when all the bonds of the products are formed. Careful with the signs of the energy, as the definition of bond enthalpy refers to break bonds. When we calculate the breakage of bonds, we use the given values, that is positive values, but when we calculate the formation of bonds, we need to change the sign, that is use them as negative values. Let's start with the reactants. First, the ethanol. We have one carbon-carbon bond, that requires 347 kilojoules per mole. Total 347, I will skip the units in the rest of the numbers to avoid constant repetition. We have 5 carbon-hydrogen bonds, with a contribution of 415 each, give a total of 2075. We have one carbon-oxygen bond, contributing with 358. Finally, we have one oxygen-hydrogen bond, requiring 464. Adding all these values, we have that the breakage of ethanol requires 3,244 kilojoules per mole. The other reactant that we have is 3 mole of water. Each mole of water has 2 moles of hydrogen-oxygen bond, so, we need 3 times 2 times 464 equals to 2,784. We move now to the products. We start with the hydrogen. We have 6 mole formed, therefore the energy supplied will be 6 times 435 equals to 2,610. Remember that the sign is changed, as we are forming bonds. And the last product is 2 mole of carbon dioxide, each mole has 2 double bond carbon oxygen. Therefore we are going to have 2 times minus 805 equals to minus 3,220. Adding all together we have a total of 198 kilojoules per mole. In question 4c, we are asked for the bond angles of carbon dioxide and water, explaining in terms of electron pair repulsion, why the bond angles are different. The carbon dioxide has a linear shape with an angle of 180 degrees. The carbon atom is in the center and 2 oxygen atoms on either side. There are 2 double bonds between the carbon and oxygen atoms, and no lone pairs on the central carbon atom. The electron pairs around the carbon atom repel each other equally, positioning themselves as far apart as possible, which results in a bond angle of 180 degrees. The water has a bent shape angle of 104.5 degrees. The structure of water is a bent or V-shaped structure with the oxygen atom in the center and 2 hydrogen atoms. The oxygen atom has 2 lone pairs and 2 bonding pairs of electrons. The lone pairs repel more strongly than bonding pairs. This increased repulsion between the lone pairs pushes the hydrogen atoms closer together, reducing the bond angle from the tetrahedral angle of 109.5 to about 104.5 degrees. Question 5 is about the preparation of 2-bromobutane. Its molecular mass is given. Section A refers to the preparation of 2-bromobutane by the reaction of butane with bromine. The reaction, provided, is initiated by the formation of bromine radicals from bromine. In the first question, we are asked by the conditions for the formation of bromine radicals from bromine. Halogens form radicals under UV light. In the second question, we are asked for 2 propagation steps. In the propagation steps we need to produce radicals as products. These radicals will react with other molecules that produces more radicals and so on. The easy way of doing it is using the radical of the halogen to react with the molecule to produce the radical from this molecule, and use this radical to produce another halogen radical. In the third question, we are asked for 2 reasons behind the low yield of the reaction. It is only 30%. Free radical substitution is difficult to control, and there are many reasons to justify the low yield. You can select 2 from any valid reason such as formation of 1-bromobutane, further substitution producing di, tri, or higher bromobutanes, production of different termination products, like octane, more than 1 termination step, etc. In part B of questions 5, we are given the reaction of but2-ene with hydrogen bromide to produce. We are asked to explain, in terms of atom economy, why this reaction is more sustainable than the reaction in part A. Atom economy is defined as the percentage of the molecular mass of the desired product divided by the total molecular masses of all the reactants. For the reaction in part A, reaction 5.1, we have that the molecular mass of the 2-bromobutane is 136.9, for the butane 58 and for the bromine 159.8. We can find that the percentage of atom economy is 62.9%. For the reaction in part B, reaction 5.2, we have that the molecular masses of the 2-bromobutane is 136.9, but 2-ene56, and for bromidic acid 80.9. Giving a percent atom recovery of 100%. A 100% atom economy in reaction 5.2 is more efficient than a 62.9% atom economy in reaction 5.1. In section C of question 5, we have the preparation of 2-bromobutane by reacting butan 2OL, with sodium bromide and sulfuric acid. The reaction is given. 2-bromobutane is a liquid with a boiling point of 91 degrees centigrade and does not mix with water, information that we will use in the second question. In the first question, a student plans to prepare 10 grams of 2-bromobutane using this reaction. With a yield of 67%, we are asked to calculate the mass of butan 2OL needed for this preparation, giving the answer to three significant figures. As yield is 67%, to obtain 10 grams of 2-bromobutane, we need to aim for 10 times 100 divided by 67 equals to 14.925 grams of 2-bromobutane. With the molecular mass of 2-bromobutane, we find that 14.925 grams are 0.1090 mole of 2-bromobutane. Reaction 5.3 shows that 1 mole of 2-bromobutane requires 1 mole of butan 2OL, therefore we need 0.1092 mole of butan 2OL. The molecular mass of butan 2OL is 74 grams per mole. And we can calculate that 0.1092 mole of butan 2OL is 8.086 grams of butan 2OL. Rounded to three significant figures, it is 8.07 grams. In the second question of question 5C, the student mixes butan 2OL, sodium bromide, and sulfuric acid in a pear-shaped flask, and refluxes the mixture. After 1 hour, the mixture in the flask has separated into two layers, an aqueous layer and an organic layer. We are asked to describe the procedures the student would need to carry out to obtain a pure, dry sample of 2-bromobutane from this mixture. This is a classic separation techniques of immiscible liquids. First, separate the mixture, the organic layer, from the aqueous layer using a separating funnel. Note, as we don't know the densities, we cannot say which layer will be on top and which on bottom, so don't specify. Second, dry the organic layer with an anhydrous salt, such as calcium chloride, sodium sulfate, magnesium sulfate, or calcium sulfate. Third, distill and collect the fraction at 91 degrees centigrade, boiling point of 2-bromobutane. In question 6, we have an organic compound that is unsaturated and is a trans-stereoisomer. We are given the composition by mass, the mass spectrum and the infrared spectrum of compound A. We need to determine the structure of the compound. We will go by parts. I will make space by removing some of the information and start with the molecular formula from the composition by weight. To calculate the empirical formula, I always create a table with 5 columns. The first column is for the name of the atom. The second column is for the atomic mass. The third column is for the mass of percentage of each atom. In the 4 column I calculate the number of moles by dividing the mass with the atomic mass. In the last column, I divided each number obtained in the previous column by the lowest number obtained in the previous column. The first column and third columns are filled with the data of the problem. The second column is filled with data from the periodic table. The fourth column is the division between the third and the second. In this last column, the lowest number obtained is 2.31. So, in the fifth columns we divide each number obtained in the fourth column by 2.31. The numbers obtained in this column give us the empirical formula. That is 2 atoms of carbon, 3 of hydrogen and 1 of oxygen. Coming back to the original problem, we have the empirical formula C2H3O1. Using atomic masses, this formula has a molecular mass of 2 times 12 plus 3 times 1 plus 1 times 16 equals to 43. Looking at the mass spectrum, we find that the highest peak appear at m/z 86, the small peak at m/z equals 87 is the m+1 due to the carbon 13. Dividing 86 of the mass spectrum by 43 from the empirical molecular mass, we have 2. This means that the molecular is going to be the double of the empirical formula, that is C4H6O2. With the use of the percent composition and the mass spectrum, we have found the molecular formula. Let's focus now on the infrared spectrum. This interpretation requires some practice and trial and error. It is like a puzzle. Take the data from the data sheet of the exam, the information that you have so far, and find patterns. From the data sheet in the exam, we can identify the following peaks. An oxygen-hydrogen bond broad peak of carboxylic acid between 2500 to 3300 reciprocal centimeter. A double carbon-oxygen peak at around 1700 reciprocal centimeter. A double carbon-carbon peak at around 1650 reciprocal centimeter. Anything below 1500 reciprocal centimeter is considered fingerprints. We know that we have a carboxyl group that will give us the OH peak and the double bond CO peak. We also know that we have double bond carbon-carbon, that it was also indicated with the comment that it is an unsaturated compound. The molecular formula indicates that they have 4 atoms of carbon, and we are using 1 for the carboxyl group and 2 in the double bond. We can suspect that the 4th one will be a methyl group, CH3. With this composition, there are a few options available, but as the compound is a trans isomer, the only viable option is the one on the left. And this the end of the paper. If you have any question or comment, leave them in the comments. If you have found this video useful, please click like, as it will help me to continue uploading similar videos.